Hello everyone. Alright, I'm going to demonstrate to you one problems to find the inductance for the case of two parallel wires. And if you can see from this diagram, we have two line wire which position along the z-axis, and both of the wire have a radius of A and they are separated about D. There's a distance of separations, and now we are going to calculate the total inductance that actually produced by this structure. Okay, so since we have two wires, so I think it's better for us to just focus on one wire for this moment, and then we can simply times 2 because they are identical. So let's focus on the first wire on the left hand side over here. So we have to find the L, which can actually be obtained from the formula of magnetic energy. So let me get down here. If you can recall our last lecture, to find the magnetic energy, you can use this formula half Li squared, so that you can find the L by rearranging this formula to WH over I squared. And we do know also that to find the magnetic energy, we have to find the magnetic field, whereby the formula of magnetic energy actually is equal to half integrations mu h squared dV. Okay guys, so since if you can see from these diagrams, let's look at for the first line wire on the left hand side. So here actually it covers, or actually it has two different regions that we have to consider. The first one is actually within the wire. That's our regions of interest, the first one, and then the other one is the outer wire. So the first wire, the first region, which actually will give us the internal inductance, while the other region, the outer wire, will give us the external conductance. So in short, we have to combine them to get the complete value of conductance. Right? So let's find both inductance. So as we can recall our last lecture, we have proved together that the standard or the general formula of the self or internal conductance by any wire, we can simply use these expressions. So the L internal or the self inductance for any wire, we can simply use this formula mu L over 8 pi Henry. Okay guys, so that's the formula that actually come due to the inside wire. So now we are going to find the inductance that actually comes from the outside region. Alright, so now let's find the H field that actually exists outside of the wire. So since we assume that the length of the cable or wire is much larger than the radius of wire, so we can simply assume that this is a case of infinite case, whereby we can simply apply the Ampere's second law to get the H field. So let's apply the ACL, the closed integrations. So the H dot dl equal to the I enclosed. So since we are using this law, so we have to draw our Ampere loop. So this L, guys, the L refer to the Ampere loop. So we have to draw the Ampere loops. And so let's proceed. So the H 2 pi r, and then let's say we are going to draw the Ampere loop outside the wire. So that is going to be our point, the limit point that we have to consider. So let's say that's your Ampere loop, right? Alright, so we have to find the I enclosed that actually exists within this loop. So if you can see from this diagram, the I enclosed actually is equal to the I total that flowing within the first wire, which is I. So automatically we're gonna have the H field expressions is equal to the I 2 pi in phi directions ampere per meter. Okay guys, this is our H expressions that actually can be used to find the H outside of the wire. Okay, so let's proceed to find the magnetic energy by using this formula. So we have to replace this H by this H magnitude. So this is our H magnitude. So let's put inside here so you can have the magnetic energy is equal to half mu I over 2 pi r squared, and then for the dV for the case of cylinder is standard one, which r dr dv dz. Okay, so let's expand the equations. Now you have mu over 2 I squared over 4 pi squared. Then now you have 1 over r dv dz. Okay guys, so now we have actually here from r squared, and then up here 1, so left 1 there, and take out all the constant. So now let's carefully set the limit for each integrations. For the dz, the length of the wire, let's say we assume from 0 to L, and then the pi for sure actually 0 to 2 pi. And then guys, we have to ensure that what is the limit for this R. So if you can see from this diagram, we have to consider the region that cover outside of cylinder to the other center of conductor. So it means that guys, this is our regions of interest. Alright, because we have to cover the region that cover from outside, which is from this point until this point. So in other words, we can say that guys, the limit from the R actually from A until D minus A. Right, here is D minus this distance of A. So now we have here from A until D minus A. Okay, so if you proceed to the end, you'll find that your expression will be like this. So mu I squared 2 pi L for these two part, and then for the line R gonna have D minus A over down here gonna have 8 pi squared. So let's simplify. So then we have here pi at 1, pi at there, so 2 up, 4 left down here. So lastly, you are going to have these expressions of magnetic energy. So to be mu I squared L ln D minus A over 4 pi. So let's substitute this expression of magnetic energy inside this inductance formula to calculate the external inductance as desired. So to find the external, so just 2 I squared, so let's put this one mu I squared R ln D minus A over 4 pi. So if we can simplify again, you will see that the I down here with I up there, and then the 2 up there with 4 down here, left 2. So the final answer or expressions of the external inductance would be mu L over 2 pi ln D minus A over A. Okay guys, so this is our final expressions of the external inductance. So as I mentioned previously, so we have to combine between the internal and also the external. So that would be the inductance come from first or single wire. So since we have double wire or two parallel wires, so we have to times 2 to save our time and cut down the steps. So now to find the L net that due to both wires, so just times 2 of the L internal that we obtained in previous lecture as shown here, plus the L external that we just obtained here. So let's simplify. So we have here 2, then we have here mu L over 8 pi plus mu L over 2 pi ln D minus A over A. So now let's simplify. So 2 here, you're gonna have left 4, 2 gone. So finally guys, we're gonna have these expressions, the L net, the L net or net L total is equal to the mu L pi. So let's factorize 1 over 4 plus ln D minus A over A Henry. Right guys, so if we assume that the distance of separations between these two wires is much larger than the radius of the wire, so you can see that the expression of L net will become like this: mu L over pi 1 over 4 plus ln D over A. Okay guys, so this is a case of when we assume that the distance of separations is much larger than its radius. So if you want to find the inductance per meter length, so just replace the L here is equal to 1. So you can find here the L per meter length is equal to the mu pi 1 over 4 plus ln D over A. Now we have unit Henry per meter. Okay guys, so that's the idea how we can actually find the inductance. So let me summarize again. So for this case, we have two parallel wire, which both of them will have their own inductance value, and the inductance actually guys is composed of two value, which are the first one come from the internal or the self inductance, and the other one actually come from the external value of inductance. So it just add up both of them and just times 2 to find the total inductance that due to this particular structure. Okay guys, I hope you can try yourself, and all the best for your study.